break, and then as soon as school was supposed to reopen, we had 2 snow days here in DC. So this is like my first hours back after multiple weeks of no childcare. So I'll be a little frazzled today, but that's okay. So last time, if I remember right, we discussed the bulletproofs polynomial commitment scheme, also known as IPA. This has a lot of nice properties, but some not so nice properties. Nice properties, it's transparent. There's no trusted setup. That is, the commitment key is just a bunch of random group elements. It is, I guess, you could call it a bad thing, depending on your views as to the threat of quantum computers. But it does use cryptographic groups. So it is not a post-quantum commitment scheme. But it doesn't need pairing. So its security is based on hardness of discrete logarithms, and you can kind of use any cryptographic group you want. It doesn't have to be a pairing friendly group. So you could, maybe we'll call this not so good. But the commitment is really small, so that's good. It's just one group element. The commitment is just a Peterson vector commitment, basically to the coefficients of the polynomial that's being committed. The evaluation proofs are pretty short. So just logarithmically many group elements. Here, this n here is like the number of coefficients of the polynomial being committed. So if it's a univariate polynomial, this would just be the degree of the polynomial being committed. So this is pretty short. This is like a few kilobytes or something. Certainly much shorter than like hashing based commitment schemes like Fry or what have you. So we'll call that good. But then the big downside is that verifying the evaluation proofs takes a lot of time, as does computing them. The amount of time taken is n scalar multiplications. And, we discussed in some detail last meeting, like this is actually super linear time because a scalar multiplication, like concretely, that's something like 4,000 field operations. So the verification here is something like, 4,000 n field operations or something. So it's linear with like this horrible, multi-thousand-fold factor out in front. So that's bulletproofs. And today we're going to discuss another commitment scheme, which I think is more popular than bulletproofs, although bulletproofs is deployed, for example, in Zcash, which addresses this big. So this is like the big X, the big bad thing in bulletproofs, and KZG avoids that big X. So the evaluation proofs are just a constant number of group elements. Just a handful of them, like depending on, let's just say even one group element maybe. And then verifying them is a constant number of pairing operations, which is also pretty fast. So I don't know, it's like 2 pairings or something. And so, you'll see snark verifiers running on Ethereum that are verifying KZG commitments, and it's only going to cost, I don't know off the top of my head exactly what it is, but it's well under 100,000 gas. So if you're an Ethereum person, this is, verifying these proofs is just like tens of thousands of gas, pretty cheap. Something like that. Plonk proofs as a whole, the way Plonk uses KZG commitments typically, is like 200,000 gas. And so, some fraction of that is verifying a KZG evaluation proof. The big downside relative to bulletproofs is it requires a trusted setup. So it's not transparent. So it needs a trusted setup. And it also needs pairings, although that's not such a big deal. There are a lot of pairing friendly groups that are quite popular. The most popular ones are probably BN254 and BLS 12381. BN254 has an Ethereum precompile. It has for years. I actually think one of the next hard forks is actually going to give an Ethereum precompile finally for BLS 12381. So this soon will have an Ethereum precompile. And just quick comments here. One reason people are trying to move away from BN254 is that shortly after Ethereum decided to give it a precompile, some slightly better attacks were discovered on this curve, on solving discrete logarithms in this curve. The security level of this curve it was originally thought to be 128 bits, and now it's not. So, I mean, you'll see. It's a little hard to tell exactly how efficient the attacks are. So, I think it's quite conservative to say that this curve has between 100 to 110 bits of security, whereas BLS 12381, we still believe it has 128 bits of security. Okay, so that's KZG commitments, and that's what we're going to see today. Okay, so let me pause here. Does anyone want to ask any questions about this? It's been a while since we met, so any questions in general?
None in the chat. I had a quick one. So you were mentioning before, like at the start, kind of the comparison of using discrete log based groups versus pairing situations. And what is the kind of advantage of using a discrete log versus a pairing when we know that discrete log is not quantum resistant?
Great. Yeah. So some cryptographic groups support pairings and others don't. So you have more flexibility in what group you use if you don't need pairings. And I don't think it's such a big deal. So BLS 12381, one reason it's like worse than BN254 performance wise is we've discussed how there are kind of two fields associated with any elliptic curve. There's like the scalar field and the base field. And so the base field of BLS 12381 is pretty big. So it's 381 bits. That's what the 381 means. So group operations are a little bit slower, and group elements just are kind of bigger to write down, each group element. Versus BN254 or some other. BN254 is pairing friendly. It just has this downside here that the security level isn't as high as ideal. But there are lots of other non-pairing friendly curves that we still think have 128 bits of security that have more like something like a 254-bit base field or something similar to BN254. I think where things matter more. So 381-bit base field, not great, not the end of the world. Where things matter more is when you bring in recursion, snark recursion. And there, your life is much nicer if you would like, ideally, what's called a cycle of curves. Okay, and these support like arbitrary depth snark recursions where you prove a proof and then prove that proof and then prove that proof and so on and so forth without some nasty engineering performance issues coming up. And we just don't have good cycles of pairing friendly curves. So that's the biggest downside, I'd say. Now, there are ways around this because we do have pretty good cycles where so any cycle involves two curves. It could be a longer cycle than that, but that's the simplest, nicest cycle involves two curves where the base field of one matches the scalar field of the other, and vice versa. Where one of the curves is pairing friendly and the other is not. And so exploiting that, you often can kind of use your snarks that use pairings even with deep recursions, but you have to suffer a little more. You have more headaches to make it all work out, because one of the two curves doesn't support pairings. So cycles here would be BN254 is in a cycle with Grumpkin, and BLS 12381 is in a cycle with Bandersnatch. And so if you ever look into Verkle trees, which Ethereum, was planning to, put into the base layer, and now maybe not, or maybe still hard to tell, ongoing discussion. That's all over Bandersnatch. And why is it over Bandersnatch? It's because people want to use a pairing friendly snark, which, is going to use BLS 12381 to prove they know a bunch of group elements. And so where should the group elements live if you're going to use, BLS 12381 in your snark to prove the group elements? The group elements should live in Bandersnatch. That's a lot to follow, but those are all the key issues. So to summarize, if you want a pairing friendly curve at 128 bits of security, you'll need a somewhat bigger base field than if you didn't need a pairing friendly curve. And if you want to do snark recursion, you're going to have some headaches because we don't have good cycles where all the curves in the cycles support pairings. Was that a clear enough response?
Totally. I didn't follow the bit about the cycles though. So why do we need to do the cycles for snark recursion?
Yeah, great. So you don't need to. It keeps things nice and efficient and simple, though. So here's the idea.
I don't know much about recursion, but my guess is that there's just like a lot of complicated things that can make it kind of blow up, and so you're trying to find ways to not do so.
Yeah. So the key issue is, I think, conveyable in a sentence, which is what is snark recursion? It's like you have some snark. It has some verification. So let's call it, I don't know, snark A. It has some verification procedure. So let's say the verifier is V. And to do recursion, what you do is you turn V into like a circuit, and then you prove a satisfying assignment for that circuit. Right? Because what is a satisfying assignment for that circuit? It's just a proof that the verifier would have accepted. Okay. And what's the headache? Why do you want cycles of pairing friendly curves? It's like if snark A uses elliptic curves, this verifier is going to do field operations over the base field of the curve. The base field means like the group elements are like pairs of base field elements. So it's like the verifying, snark A's proofs involve field ops over the base field. Whereas snark A would have been a snark for like circuits over the scalar field. And these are different fields. So snark A is targeted at circuits over the scalar field, but the verifier of the snark does operations over the base field. Okay. So now in order to turn the verifier into a circuit, like for that circuit to be nice and small and simple, you really want this circuit to be over the base field of the curve. Okay. But that means you need to use to prove, a satisfying assignment, for this circuit, you now want to use a snark that doesn't work over the scalar field of the curve you started with anymore, but rather you want a snark that, is for circuits over the base field. So there's this field switch you want to do when you go from, producing the snark A proof to proving the snark A proof. You want to, that second proof, you want to work over the base field instead of the scalar field. And so life is much simple if you can come up with two curves, like a curve, I call it curve A and curve B, where, the scalar field of curve A is the same as the base field of curve B and vice versa. Yeah, so let me scalar field. base field. And so that way, this second proof, that this recursive proof, can just happily, work over curve B. And then when you want to recurse on that, and so you take the snark verifier for your snark over curve B and turn it into a circuit. That circuit you want to be over the scalar field, and then when you prove a satisfying assignment for that circuit, you can work over curve A again, and you just go back and forth between the two curves. So that's the key issue. The key, to summarize, the one sentence I was getting at is when you want to do snark recursion, it's best if you have two curves, where the base field of one matches the scalar field of the other. That's what's going to let you efficiently turn your snark verifiers into circuits and then prove the circuit. Was that somewhat helpful?
Yeah, nice. No, that's really interesting. That's really cool. I think it's interesting that like they can even find groups that have those numbers match up, but I guess.
Yeah, no, I mean it's a bit of an art, and like we just don't, we don't have that many examples, and there have every time you want another one, some expert has to go and like do a machine search for curves where it looks like the discrete log in the group, but the base field is the right field, and blah 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 blah.
And that's actually how they come up with some of these curves, is like machine searches.
All of this
cool.
is machine search.
Yeah, cool.
Great, thanks for the questions. Other questions?
Still none in chat.
Okay, great. All right, so let's dive into.
Sorry, there is a quick question. So the question is this different from folding, the recursion that you're talking about?
So folding uses recursion, but there are like folding is like a very efficient way to do recursion, where you keep you kind of avoid having to turn the entire snark verification procedure into a circuit. And so the circuit you prove recursively is just much smaller if you're doing folding. But there are other ways to do snark recursion that isn't folding. So just think of folding as like a really, really efficient way to do recursion, but you could just, what I described is sort of a more brute force, take the whole verifier, turn it into a circuit, prove you know a satisfying assignment for that circuit. That's not folding. That's just what we call brute force recursion. Yeah, but so folding schemes run into this issue where they need a cycle, and so if you want to run you'll see people like implementing Nova over this BN254 Grumpkin cycle, right? And the reason they're using this cycle is because they kind of want the final proof that goes on chain to be use KZG commitments that we're going to cover today, so that the verification procedure is like really fast, and the proofs are really short. And so they'll use this cycle so that you kind of wind up at the end of all the folds over BN254, and then you can apply Planck or something. So folding is sort of a very advanced way of doing snark recursion, but there are less advanced ways of doing snark recursion. More questions?
Were there drawbacks here of folding over recursion? It kind of sounded like folding is just a better recursion.
I'd say
is it harder? I mean, sometimes that's the drawback. Is it just like it's a harder thing to do when it's not always failed?
Yeah, it's more sophisticated. That one way to say it is in order to avoid. Let's just say it's more sophisticated, and so if you're building like a folding scheme from scratch, today, like if you're implementing it, your life is going to be more complicated than just like take this snark verifier and turn it into a circuit. Even the process of taking a snark verifier and turning it into a circuit is like more painful today than we would like it to be. You might have to even today like write the verifier in circom, which is not the nicest thing and is like a very error prone process and stuff. But if you're building a folding scheme, you're going to like really need more expertise even than the ability to like write circom. So you'll need more expertise. The computation you're applying the folding procedure to sort of needs a nice form, and that form is universal. But if you you just have, there's a lot more glass to chew for sure. And that's part of what, like, my view of why folding schemes haven't taken over the world today. A big reason is just all that glass you're going to have to chew. I think some people have gotten so frustrated they think that folding just like doesn't work well, and I don't think that's the case. I think there's just a lot of glass to chew, and we're not the best yet at chewing the glass. But anyway, so hopefully that's some helpful color. I think folding still will take over the world. Like, it's at the center of the Jolt roadmap because Jolt is using elliptic curves today, and the most efficient way to do recursion once you're using elliptic curve commitments is to do folding. That keeps the overhead of folding minimal.
So since we're here, and I'm kind of curious, like, can you speak to this, like, cutting glass a little bit? Like, what about folding sucks so much or is hard?
Yeah. Okay. So how do I want to say this? So what folding is doing? Yeah, this is a little hard to say without risking
We
getting.
don't need to go into it. It's fine.
Okay, I think I can say I'm going to limit it. Cut me off if I go for more than like
Deal.
1 minute.
Deal.
Okay. So snark verifiers do a lot of stuff, right? Like verifying polynomial evaluation proofs is one thing that they do. Okay. But it's often the most expensive thing they do. Okay. So what folding schemes do is they say, look, I am not going to take like verifying evaluation proofs and turn it into a circuit, because the circuit would be really freaking big. So rather what they do is they'll take evaluation proofs and they'll just defer. Well, they'll leave them out. So they'll take polynomial commitments, and they just won't prove the claimed evaluations. But these group-based commitment schemes like bulletproofs and KZG and stuff, they come with really efficient batch like amortization procedures. You also call it accumulation or deferral. So you can take like a bunch of KZG or bulletproofs commitments, and rather than verifying one evaluation proof for each of them individually, you can just sort of homomorphically combine them into a single commitment and check one evaluation proof, for that one combined commitment. And so that's basically what they'll do, these folding schemes. So the work Halo, like, this was exactly the perspective. They were like, we're going to, in recursion, we're going to turn everything that the snark verifier does but evaluation proofs into a circuit. We're kind of going to recursively prove that circuit, but we're still left to, deal with these evaluation proofs. And those we're going to deal with via batching. You're kind of going to, just munge all those commitments together and provide a single evaluation proof for all of them. And
Nice.
just
You're at your minute.
I'm at my minute. Making that all work out is just a big pain.
Cool.
I'll just leave it that way. Okay. All right. So let's dive into KZG commitments. Okay. So let's talk about what the commitment key is. So this powers a tau trusted setup thing that has come up many times in questions, but this is the first time we're seeing actually why it comes up. And so the idea is, well, so let's say someone out there in the world picks a field element, from the scalar field of the elliptic curve, the pairing friendly elliptic curve group you want to work over, a field element tau at random. It's key that no one in the world knows tau. So this is called toxic waste. If anyone in the world knew tau, they could break binding of the KZG commitment scheme and thereby, come up with convincing snark, proofs of any statement they want. So the soundness of your snark depends on no one knowing tau. And so the commitment key is, okay, so let G be a random group element. in your pairing friendly group, BN254 or whatever. So the commitment key is powers of tau in the exponent. Okay, and so let's say here n is, KZG commitments only apply to univariate polynomials. So here n is the degree of the polynomial you want to commit to. Okay, and so we've designed, basically MPC protocols that let like hundreds or thousands of people all kind of contribute their own personal randomness to select tau, and that ensures that only if all of those participants got together and they each kind of have their personal share of the toxic waste, and only if they combine all of their personal shares can they actually figure out what tau is. So it's a pretty mild trust assumption. It's very controversial, like how mild is it really? But my view is focusing on that as a threat to your snark soundness is a little bit misguided. Where like today, like bugs are a vastly bigger threat than the possibility that thousands of people all got together and put their toxic waste shares together to figure out tau. When some of those people are from competing ZK projects and blah 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 and stuff like that. So I don't have like a dog in this fight really, but that's the context for this trusted setup here. So anybody who wants to commit to polynomials with KZG commitments, they need to know this key here. So this is the commitment key. And people have run trusted setups. I think the biggest I've seen. It's a project called Perpetual Powers of Tau, which I think was sponsored by the Ethereum Foundation. Has 2 to the 29, which is about 500 million powers of tau. And I think it had several hundred participants. And so, just keep in mind, like, writing down 500 million powers of tau means, the commitment key is, like many gigabytes of data. It's a giant list of group elements, 500 million group elements, 32 or 64 or whatever bytes per group element. So it's gigabytes of data just to download this key. And probably each one of the hundreds of participants, that participated and generated this key spent, a non-trivial amount of time computing their contribution to this key because the key is just so big. Okay, so that is the powers of tau trusted setup used by KZG commitments. In my view, the biggest downside, because I'm not so worried by like this trust assumption about the toxic waste stuff. But what is annoying is that this commitment, if you want to commit to polynomials with under 1 billion coefficients, you need to download this commitment key, which is many gigabytes of data. That's going to preclude doing it, any proving on a phone. So it just severely limits the sizes of the statements you can prove having this commitment key. Now, Bulletproofs also has a commitment key that's just as big. It's just, there's no toxic waste. So, size of commitment key, I think, is sort of a under discussed, downside, let's say, of curve-based commitments, right? Hashing-based commitments, they have much bigger evaluation proofs, so that's their downside. They're also post-quantum, so that's a upside. But another upside is just the commitment key for them is just like one hash function. It's like, hey, we're going to use SHA, whereas the commitment key here is, many gigabytes of random looking group elements. Okay, so that's the commitment key. And so, in order to commit to a polynomial, let's say it's a univariate polynomial. Let's call its coefficients C0 to Cn. So the commitments to P with KZG commitments, it's just Peterson vector commitments to the coefficient vector, where the commitment key is the powers of tau SRS. SRS stands for structured reference string. It's another phrase for commitment key when the commitment key was generated via this trusted setup. So the commitment key is just this inner product of the coefficient vector and the SRS. Maybe I should give the SRS a name. I'll just call it SRS. Right. So, here I'm using additive group notation. So that would be CI times G to the tau to the I. But of course, the committer doesn't know tau. So this just looks like, let me call this HI. So, the committer, who doesn't know tau, like it just sees this key, like G, I could just call it H0, H1, H2 up to HN is the SRS. And like it knows that each HI is G to the tau to the I, for some tau, but it has no idea what tau is. So anyway, so this is literally the same as the bulletproofs commitment, same as bulletproofs, except the commitment key now is structured instead of uniform random group elements. It's just a different commitment key. Okay, so any questions about that? All right, so again, so the commitment key, it's the same as bulletproofs. It's just now the commitment key is this structured reference string instead of a bunch of random group elements. Okay,
so two questions out of chat. The first was, are there any constraints on G? And then the other is, should P of X be in multiplicative group notation?
Great. Okay, so restrictions on G. I mean, G should be like a randomly chosen generator of the group. I believe that all the groups people use are cyclic. So like you just pick a random group element and it is a random generator of the group. So just think of G as like, people used a cryptographic PRG to select one group element at random, and that's what G is. It is
in some cases, though, the group is actually like a subset of the full elliptic curve group, right? Like we've taken a cyclic subset. It's not the elliptic curve group itself was cyclic.
Yeah, that's all correct. And I try not to go into those details. And if you push me into that, I'll probably make a mistake. Yeah. So in practical implementations of curves, you're totally right. It's like the curve actually used is like a cyclic subgroup of a non-cyclic, slightly bigger group. Though I don't think those details like matter at all for understanding.
I think we just say our cyclic subgroup, right? Like we just say the cyclic subgroup. That's all we care about.
Yeah, I think you're right. If I just said, we always use a cyclic subgroup of the elliptic curve group, everything I said would be completely correct. Yes. And then the other question, you might need to repeat it since I'm so out of it today. Should I use multiplicative notation?
That's right.
Yeah, so that is just a convention choice. I do prefer multiplicative notation. The additive notation is nicer with things like bulletproofs because this inner product notation just gets really nice. KZG commitments, I think the multiplicative notation works fine. So let's actually switch over to multiplicative notation now. So thank you for the question. I will use that as an opportunity to switch, even though it sort of doesn't matter. And so now I'll write the commitment as a group product where the coefficients are exponents. So this would be H sub I to the C sub I. Now, if you want to, so this would be the commitment. Now, it is a little bit, I think, conceptually helpful to remember, even though no one knows what tau is, there always is some tau, so that H sub I is G to the tau to the I. So that's what's getting raised to the CI. And then that is the same as G raised to the power CI times tau to the I. And so now this is interesting and nice. It's a nice way to think about KZG commitments. So again, thank you for raising the question about, should you be using multiple group notation? Stuff actually gets nicer for KZG commitments if I do. This is the same as I'm going to do one more simplification. So I'm going to move this group product, into the exponent where it becomes a sum. So this is the same as G to the sum over I of CI times tau to the I, which finally has this nice simple expression of as G to the P of tau. Okay, so this is something that's so cool, and which KZG commitments exploit, which is, I'll write this out in words, like, remember, no one knows tau. If anyone does, then security is out the window. No one knows tau, yet basically because of homomorphism, yet the committer was able to evaluate the polynomial it's committing, P at tau, in the exponent. And this is why I tend to prefer multiplicative notation, because I like to think about things happening in the exponent, and kind of no one knows what the exponents are, but interesting stuff is still happening, to the exponents. So the commitment, another way you could think of it is the committer is taking the polynomial it wants to commit to. It doesn't know what tau is, but it's still able to evaluate that polynomial out tau and stick it in the exponent. And that's what the commitment is. But functionally, because it doesn't know tau, the way it had to do that was to go through, this is called so the way I wrote it here, this is sort of what the committers, from the committer's perspective, it doesn't know what tau is, it just knows these HIs. This is called a multi-exponentiation, or an MSM, multi-scalar multiplication. Same thing, just different terminology. It had to do, because it didn't know tau, it couldn't just say, hey, I'm going to take P and evaluate it at tau and stick it in the exponent. It had to do everything via, this MSM, which is much more expensive than just evaluating P at tau directly and sticking it in the exponent. But nonetheless, in the end, it did all that work, and it was able to figure out, P at tau in the exponent without knowing tau. And so that is the commitment.
Got a question?
Yeah. Hello, can you hear me?
Yep.
Great. Speaking about this tau, and you said that we basically evaluating the polynomial at the point tau. I have two similar questions. The first one is it basically does it count as a commitment opening, since we evaluating the polynomial at the point?
Yeah, it doesn't, because an opening would be the verifier says, hey, I want to evaluate the polynomial at this point that I care about. And the prover comes back and says, hey, here's the evaluation, and a proof, that it's the right evaluation. This tau, no one knows it, not the prover, not the verifier. And so it's not like an evaluation or of P, in any cryptographic sense. In fact, it is a commitment to P. Once the prover sends this one group element here, it's sort of stuck with P, and it can't, go back and change P anymore. Did that clear things up? Sort of.
Not
Not really.
Yeah. I mean, the other question was that considering the number of openings of the commitment in a protocol that we are working with, we are doing this trick with blinding it with uh, a proper degree of blinding polynomial, if I recollect everything correctly. And this other question was about if such blinding uh, is meaningful only for zero knowledge flavor uh, of protocol, and for succinctness, or for just when we only care for about succinctness, is it not used at all?
Yeah, that's right. That's right. Yeah. So I have described here like unblinded KZG commitments. Blinding is only needed if you care about ZK. So if you wanted to blind the commitment, then the commitment to P would be you would take the commitment so let me call it, I don't know, commitment blinded. It would be the commitment I had before, but then the prover would pick a random field element R, and there'd be like another random group element. I don't know, let me call it G prime, and it would just multiply the unblinded commitment by G prime to the R, and that would blind it. It would be equivalent. Yeah, let me just, so that would ensure that the blinded commitment is kind of a random group element, independent of the committed polynomial, where the randomness is coming from this random choice of R. And then on top of that, I haven't told you what KZG evaluation proofs are yet, but you'd have to so this makes sure that the commitment leaks no information about P. You'd have to modify the evaluation procedure as well to make sure the evaluation proofs reveal no information about P. And you can do all this, but it's, I like to ignore it. If you only care about succinctness, you don't need to worry about it at all. Does that make sense?
I see, and just one small thing, connecting the both questions. I mean, uh, when we do this, when we choose to do this blinding, uh, should we account in should we account for this evaluation at tau in the degree of blinding polynomial?
Yeah, that's a great question. Yeah, so I think yes. But I've never looked in the weeds of blinded hiding KZG commitments. I do know that the simulators people give when they work through these details, the simulator itself knows tau, I think, which is very much suggesting that you know you do have to take that into account. I mean, in general, it's sort of this funny thing where like no one knows tau, so like what could G to the P of tau possibly leak about P? You've evaluated P at a random point, but no one knows what that random point is. So why, how could it really be, real information about P? I think if you want perfect zero knowledge, you have to worry about it, and possibly, I haven't looked through the details. Possibly even if you want if you're happy with some computational analog of ZK, you still have to worry about it. So yeah, it's like, to me, intuitively, it feels like G to the P of tau is not really leaking anything about P because no one knows tau. But I think that's not a formal statement, and in fact, I think the intuition is just wrong if you actually go through the trouble of defining a simulator to formally, rigorously, establish ZK. Is that a little bit helpful?
Yeah, it's very interesting and makes a lot of sense. Thanks a lot.
Yeah, and so if you want a pointer, the paper Zeromorph is looking at a multilinear analog of KZG commitments, and they very, very, very much care about zero knowledge. This paper came from Aztec. Aztec is a privacy-focused project. They need ZK, And so I know they had to work through a lot of these details about, zero knowledge with KZG commitments. And the paper is not old; it's from the last couple of years. And I think some of that suffering, they had to do novelly. And I don't think all of the suffering was just coming from multilinearity being what they cared about. I think some of it was like, even in the univariate case, people haven't done all the full suffering in full detail, I think. So anyway, so I would suggest you have a look. It's a very nice paper, and it definitely goes through all of the details of all of the issues you have in mind.
Sometimes I feel like they do this additional degree accounting for evaluation at tau just to be on the safe side.
Yeah.
Uh,
So I have that sense too, but until you actually have a simulator, you don't know it's CK. So my intuition there that it's like not really necessary could be completely like I don't trust that intuition in the slightest. Yeah.
so this one additional degree doesn't add a lot of burden in real zero knowledge case.
Yeah, I don't think it's much performance overhead, so you might as well do it too. In addition to, you should, it's not. Yeah, I don't actually think it's like overly conservative, but I don't think it comes with any performance price. So just do it.
I see. Thanks a lot. It's insightful. Thank you.
Yeah, thanks for the questions. Okay, so let's talk about evaluation proofs. Yeah, so reminder: the commitment to P was G to the P of tau, but no one knows tau. Now, the evaluation proofs are based on the following fact. So if the verifier says, "Hey, I want to evaluate P at this point R that I care about," and the prover says, "Hey, I claim that P evaluated at R is T." Okay, so this holds if and only if P of R. No, how do I want to? I'm going to mess this up. So we want to get a 0 over. So it's P of X minus T is divisible by X minus R. Right. And so in other words, P of X minus T over X minus R has degree n minus 1. Okay, and what's happening here is I don't want to bother formally proving the fact. It's very simple to do, but think about what happens if you plug in R for X. You get P of R minus T up here, which if the prover is honest, so that's what the numerator gives, at R. So it gives P of R minus T, and if the prover is honest, this is 0. Okay, and the denominator is R minus R at R, which is 0. The denominator at R is 0. Right, and so anything non-zero over 0 is a problem. That's what this fact is basically saying. But 0 over 0 is like not a problem. And so very simple fact. I'll let you prove it as an exercise. But yeah, so the provers claim that P evaluates to T at R is equivalent to, if you subtract T from P, it becomes divisible by X minus R. And intuitively, it's because this fraction turns into 0 over 0 if and only if the prover's honest. 0 over 0 does not mess up any divisibility claim. Okay, so as a result, here's the evaluation proof. So let W of X be this degree n minus 1 polynomial. P of X minus T over X minus R. If the prover's honest, it's the degree n minus 1 polynomial above. And the evaluation proof is just the commitment to W, which remember is just G to the W of tau. Okay. And now the idea to verify the evaluation proof. So, the prover is sort of claiming this is all an intuitive, this is not a rigorous, proof of security of the evaluation proof procedure. But, intuitively, the prover, sends W of tau in the exponent. And the prover's claim is that, so it's that X minus R times W of X equals P of X, right? That's what the claim is intuitively, right? This is what it means for P to be divisible by X minus R, and that is dividing by X minus R, yielding a degree n minus 1 polynomial W, right? And so the verifier wants to check the claim. So the verifier wants to check this equality. And, how do we do that? In snarkland, whenever we claim that two polynomials are the same polynomial, the way we check it is we pick a random input and confirm the equality holds at that input. Right. And then, because two low degree polynomials can only agree at a small number of points, if they're not the same polynomial, that they're very, very unlikely to agree, even when you only evaluate them at one randomly chosen point. And so the verifier winds up checking this equality at the random point tau that no one knows, right? So intuitively, again, this is a very hand-wavy intuitive description of how KZG evaluation proofs are working and why they're secure. Because no one knows tau, we can just treat it like it's a completely random field element. And so the verifier, is going to check that tau minus R times W of tau equals P of tau. Okay, that's the KZG verifier check. Okay, now how does it do that? This is where the pairings come in, right? Because the prover didn't send P in full. It sent or even P of tau because no one knows tau. So what the verifier knows is not P of tau. It knows P of tau only in the exponent. And similarly, the verifier doesn't know W of tau, but it does know W of tau in the exponent. Okay, so this is where pairings come in. And so probably I should have started today by reviewing pairings, but now I'm going to do the review on the fly. So quick review of pairings. And if you haven't seen pairings before, it won't be reviewed. That's okay. So pairings just give a way for the like a verifier to be sent, let's say 3 group elements, G to the A, G to the B, G to the C, and check. So the verifier wants to check, does C equal A times B? Okay. And now, it can't just check it directly because it doesn't know A, B, and C. They're all hidden in the exponent. So what pairings do is they let the verifier do this check anyway. So a pairing, we denote the pairing operation by E. So this is just a map that takes as input like 2 group elements and spit out a 3rd group element. And I won't go into the intricacies that, actually these 3 group elements might be in slightly different groups. Don't worry about it. So a pairing is just a way, it takes 2 group elements as input and spits out a 3rd group element. And so checking whether C equals A times B is equivalent to checking whether the pairing evaluated at G to the A and G to the B spits out the same thing as evaluating the pairing at G to the C and G. Okay. So that is my, 1 sentence overview of pairings. That's all you need to know about pairings to understand snarks. I often get the question, like before I, check out the PASIC book, should I, understand how pairings work? What is this map E? And I'm like, I don't know what E is. All I know is that you use it to, if you want to know whether C equals A times B, when A, B, and C are hidden in the exponent, you use the pairing and that's it, So that's what pairings do. That's why we need a pairing friendly group with KZG commitments, is to exactly do this. So when the verifier wants to check, does this equality hold? What it does is it checks, does the pairing evaluated at g to the tau minus r, and you might be worried the verifier doesn't know tau, but it's okay. As I'll explain shortly, it's because tau's in the exponent here, and it does know g to the tau. So it sticks tau minus r, in the exponent for the first thing in the pairing. It sticks w a tau in the exponent for the second thing in the pairing, and it asks, does this equal the commitment, which was g to the p a tau, comma g. So that's what the KZG verifier actually does, right? So it wants to check this, but it can't because it doesn't know tau or w of tau or p of tau, but it can check it anyway because of the pairing. And why is the pairing enough? It's basically because there's only one multiplication here. And that's exactly what pairings let you deal with. It lets you kind of check one multiplication in the exponent. Okay, so how does it get, g to the tau minus r? Well, g to the tau is part of the commitment key. And in fact, the verifier doesn't need to know any of the commitment key other than g and g to the tau. So there'll be a verification key for KZG commitments, which is really, really short. It's just g and g to the tau. And you can get g to the tau minus r by taking g to the tau and just, multiplying it by g to the r, inverse. That equals g to the tau minus r. So, when I write g to the tau minus r here, the verifier gets that by taking g to the tau, which is part of the verification key, and multiplying that by g to the r inverse. That's KZG commitments. That's it. Okay. So maybe I should summarize again the evaluation proof. So the prover, sends the commitment to this divisor polynomial w. So it sends g to the w tau, and the verifier just checks, does the pairing evaluated at g to the tau minus r and g to the w tau, does that equal e of the commitment, which was p a tau in the exponent, comma g. That's it. Okay. So the evaluation proof required one extra MSM to commit to W, and two pairings on the verifier side. Okay, questions?
Is computing pairings usually expensive?
Yeah, it's not cheap. So one pairing, I'll tell you.
These are the ones that have pre-compiles on Ethereum, right? Which is why they're viable.
Well, so yes, they have precompiles. Yes, if they did not have precompiles, I don't think they'd be viable. But I will caution, the gas costs people assign precompiles is meant to be commensurate with the actual runtime of the operation on real machines. So the point of having the precompiles is just the following. How do I want to say this? It's like if the EVM is some, very simple VM. And so there are some things that would be very fast on your laptop, but if you had to do it via the EVM, it would be pretty terrible. And so pairings are an example of that, because they involve all these weird, field operations and stuff, which are not native to the EVM. And so, yes, these pairings have a precompile, but what that is ensuring is that when the snark verifier verifies KZG commitments on chain. The gas costs are commensurate with like what it would actually cost to run that procedure on like a CPU. Is that clear?
Yeah.
So like on a CPU, like evaluating this pairing is like a millisecond or something. I don't know. So it's not like expensive in an absolute sense, is what I'm trying to say. So one pairing is equivalent in cost to like 10 scale applications. And so let me remind myself, a scale application is something like 400 group ops, and a group op is something like on the order of 10 field ops. So this would be 10 times 400 times 10 field ops. So this is, what's that, 40,000 field ops. So it's, and a field op in these big fields is like, I don't know, 80 CPU cycles. So you're talking several million. Is it several? Yeah, 400,000 times 8. Yeah, so like 3 million CPU cycles. And your modern CPUs do like 3 billion cycles per second, right? Okay, so that's what we're talking about, like basically nothing. But as far as gas costs go or whatever, it's not literally nothing. Yeah, does that make sense? So yeah, it's pretty good that a verifier only does like 2 pairings. Like that is not a terrible thing in this. Yeah.
Yeah, super important distinction. Like it's actually not that much computation, but in like very limited environments, it's kind of too much. But yeah, I totally get what you're saying. Thanks.
Yeah. So like if you're verifying, like thousands of, KZG based proofs, every second, you're going to start having problems. But if you're verifying like, several a second or something, that's not like a big deal for most systems or, something like that. Yeah.
And Scott, hopping up. We have another question coming.
Yes. I guess I managed to unmute myself. Speaking of W at tau, uh, did I get did I get right that you said that prover needs to commit to it?
Mm-hmm. Yes.
And
Yeah, that's right. It's G to the W at tau is what it sends, and that's effectively just a KZG commitment to the polynomial W. Yes.
w- I'm just having a little bit of hard time to understand. Do we have KZG commitment inside KZG commitment?
No, I don't think so. I mean, it's just the evaluation proof. So you KZG committed to P, and then when the verifier says I want to evaluate P at R, the evaluation proof is a commitment to another polynomial whose degree is 1 less than R. And then the verifier does this simple pairing based check on the two, things, the 2 commitments it received, one for W and one for P.
And how do we know that this G in the power to W at tau is correct? Isn't just
Yeah, so I haven't established, security rigorously. I just said like, here is the check that happens, and intuitively it's confirming that this, equality of polynomials holds at tau, and you should think of tau intuitively as like just a random point. But to rigorously establish security, you would have to do a whole analysis, which I will say a little bit about momentarily. That would, that basically the analysis itself answers your question, like, that the prover must have like had no choice but to take the correct polynomial W and, KZG commit to it with the correct, commitment key. Yeah. Did that?
That's great. I just got a little bit confused along the way.
Okay.
Great.
Great.
Thank you.
More questions? Okay. Okay, so that's
Sorry,
KZG.
one more. So in order to prove that P of R equals T, the prover first needs to find some W of X and commit to that. And it seems like the prover needs to do that extra work. And I think the answer here is that not that the provers, I guess the prover is doing the extra work of calculating W, right? They have to do that like polynomial division to calculate W, but it's not a lot of work. And because the prover knows the polynomial P, like they can do the work easily.
Yeah, great question. Polynomial division is, in general, when you divide like a degree blah thing by a degree blah over 2 thing or something, that's pretty expensive and takes, FFT like algorithms. But when you divide, a P by a degree 1 thing, it's actually really fast. And so, so the prover itself does have to, do some field operations to compute this W, but that's not a bottleneck. Now, I'm glad you asked about the prover cost of, computing W and committing to W, because there is something important to point out there, which is imagine for a second all the coefficients of P are small. So I'll say all the coefficients of P, are in the set, I don't know, 0, 1, up to 2 to the 16 or something. Okay, so then committing to P is actually really fast, basically because, committing involves this big exponentiation, multi-exponentiation, and so when these exponents are small, it's much faster, right? Like we talked about this last week, I think, or last meeting. Like computing HI to the 1 is like way faster, than computing HI to the like 2 to the 256 or something, right? We're seeing more and more snarks. Typically, they have to use the sum check protocol to achieve this, but more and more snarks where all of the committed polynomials have this property, and so committing is really, really fast. Okay, so what's important? The point I want to make is even when that's the case, W of X does not have small coefficients. Right. So, you can take a polynomial that does have small coefficients P, and when you divide it by X minus some random thing, you just, the coefficients, of the result are just, all like random field elements basically. Has, nasty like, coefficients. And so that will actually make committing to W in this case more than 10x slower than committing to P. Computing these. Okay, and so what you would find in this context would be that computing the evaluation proof is like by far the prover bottleneck. But there are ways to address that. They should be better known, although they are known. So like we have to deal with this in Jolt today. We're using a multilinear analog of KZG commitments. And so we would run into exactly this issue. And so like, rather than taking, like the coefficients of P as one giant vector of length, n or n plus 1 or whatever, and just committing to that, because then the evaluation proof would be, super slow. What we do instead is like kind of a combination of Hyrax and KZG. We, kind of write the coefficients. Today we actually just have like 80 columns, something like that, of length like n over 80 each, and we commit to each individually. And then we do this batching stuff I was mentioning that the folding schemes also exploit, where rather than producing an evaluation proof individually for each of them, we have the verifier wind up taking some kind of random linear combination of them. So these all get sort of collapsed down into a single commitment, and we only open up the size n over 80 thing. And, that this divided by 80, more than offsets the 10x slower thing. And that way, evaluation proofs are not bottlenecks. Although even today in Jolt, the evaluation proofs, this is, again, a multilinear analog of KZG, but there's still like 15% approver time, even today, where we're doing this divided by 80 thing. So, anyway, I hope that was clear. So, thanks for the question. Computing W is not a big deal. Committing to W can be, because the coefficients of W will be like arbitrary field elements, even if the coefficients of P were not.
You mentioned that you are doing in Jot multilinear analog to the KZG, and I just wondering if it some kind of your version of zero-morph that you referenced earlier, or is it something completely different?
Yeah, it's very similar to zero morph. So it's something called hyper KZG, which I don't think it has a paper associated with it yet. It will at some point. But it's from Srinath Sethi and some folks at Microsoft. Very very similar to zero morph. The main difference is, I think zero morph, the verifier does 3 pairings. And for hyper KZG, it's only 2 pairings. That's all. So we also have zero morph in the Jolt library support for it, and so they're very similar in performance and ultimately what they're doing. So yeah. And zero morph is hiding and zero knowledge and all that, and hyper KZG is not ZK. So that's but we don't care about ZK right now. In Jolt, we're going to get ZK through we'll like add it on at the end once we're ready to, once it's mature.
Let's see. Thank you.
Great.
There was a question about whether this was like an amortization of proof cost, although I'm not perfectly sure what it was referring to. Is that some kind of amortization with multi-proofs?
Yeah, it's I wouldn't call it. It's just sort of a standard technique to so it turns out that this is important stuff to know about when you're dealing with bullet proofs and KZG, that these batching properties. So there are different kinds of batching you might want to do. One is commit to many polynomials and evaluate all of them at the same point. Okay, one is, another is commit to one polynomial evaluated at many points. Okay, and the third is commit to many polynomials and evaluate each of them at a different point. Okay, and so what, the batching procedures available to you and how efficient they are vary. Okay, and this setting up here that we're using in Jolt today is in this first context, and I think I actually cover this in the book somewhere, maybe chapter 16, like the final chapter on polynomial commitments. It's very simple, and yeah, what's going when you do this, like I'm not going to commit to like all the coefficients as one giant vector. I'm going to split that vector into 80 pieces, commit to each of the pieces. You wind up needing to evaluate each of the pieces at the same point. Okay, and so it's a very simple. I guess it's not worth even though it would only take a few minutes covering here, but it's a very simple procedure whereby you wind up only having to produce a single KZG evaluation proof for a certain linear combination of these 80 commitments. So this W of X, you provide one W of X, it has size n over 80, and that's all the prover has to commit to. So I guess just a couple comments here. This is not widely known. If you're in the multilinear case, there's a totally generic batching procedure. This third situation is the most difficult, right? Because you have many different polynomials and many different points. And there's a totally different generic procedure using sumcheck, which keeps getting rediscovered, actually. And anyway, to handle case 3, which is the most general case. So you basically, you apply sumcheck once, and at the end of that, you apply sumcheck to the claimed evaluations, and at the end of that, you have to evaluate a single polynomial, which is some kind of random linear combination of each of the committed ones.
Just to clarify, it sounds like he was asking about evaluating at multiple points.
One polynomial at multiple points.
Yep.
Okay, so yeah, let's see. I see. Okay, let me just think first. What are the batching procedures in that case? So firstly, just to clarify, that is not the setting I was describing up here. This turns into evaluating 80 polynomials each at the same point, not one polynomial at many different points. If you're interested in one polynomial at many different points, I think I'm not going to come up with the procedures off the top of my head, but there are procedures known for that are, I think, not. So I think there are maybe even entire papers on multi KZG proofs, and I think that's the setting they're looking at.
But independent of actually doing actual batching, you still just, one of the ideas you're kind of getting across with this is you commit to that polynomial, you give someone that commitment, and then you can give them sort of infinity evaluations afterwards. You don't need to give them anything more about the original polynomial.
Well, every evaluation does have to be. It has to be proved at some point that the evaluation was, is the correct one. Is actually the polynomial at the requested point. The question is, if you're naive about it, it's for every requested evaluation of every committed polynomial, the naive thing is just to produce a different, totally separate KZG evaluation proof for it. And that if there are a lot of evaluation points or a lot of polynomials or whatever, that's going to be a big proof, and it's going to be expensive for the prover to compute all those proofs. It's going to be expensive for the verifier to check all those proofs. And so it's often the case that you can avoid, do better than that naive thing, but how much better you can do depends on context. And so where I got into this, aside, which has gone on way too long, there's a lot of different, permutations of the context, whether you have many polynomials at one point, one polynomial at many points, or many polynomials at many points. That's one issue. Another issue is, are your polynomials multilinear or univariate? Okay. And it's in both settings, life is nice and simple if you're looking at many polynomials at one point. In both univariate and multilinear settings, that's the easiest thing to deal with. If you're in the multilinear setting, even the most general thing turns out to be pretty easy to deal with, although it's not widely known. Okay. If you're in the univariate setting, I think both 2 and 3 are somewhat painful, and there are entire papers written about them. So I'll just leave it at that. And so in what I was describing up here, which we do in Jolt to keep the evaluation proofs of KZG from being a bottleneck, that is sort of the easy setting for 2 reasons. one is it's many polynomials at the same point, and that's just generally easy. But another is these are multilinear polynomials, and that's also generally easy. Where things get complicated for the batching stuff is when you have univariate polynomials and you're in situation 2 or 3, then you start having to invoke entire research papers to do better than the naive thing.
Speaking speaking about the third one, question that you were describing, and this procedure that you mentioned with two sound checks, it on this level, it sounds very similar to what you were saying about bulletproof itself, since you were showing us uh, how bulletproofs are a couple of subjects.
Yeah. I mean, the stuff gets pretty self-referential. In different ways. I will say I don't think the fact that bulletproofs is some check is equivalent to what I said here about batching in the most general situation. But it could deserve further thought. Maybe I'll just leave it at that. Here it's like a very, it's a very special. So what's going on? Just to give a little more color on this generic thing here, apply some check. What's going on is that each evaluation query, like the claim that P of R equals T, right? That's an inner product. That's the claim that the coefficient vector of the polynomial inner product with like the powers of R. So here's this coefficients of the polynomial. Here this is powers of R. Equals T, right? Evaluation queries of polynomials are always like a special kind of inner product. And so
for understanding, just for better understanding, does this procedure equally applies for KZG and bulletproofs? Is it that generic?
Oh yeah, it's completely generic. Yeah, this just uses some check in a completely generic way to reduce a bunch of evaluation claims for to a single one basically. And what's going on, like some check, like the cleanest application of it is exactly what I said in bulletproof. So again, like what you just said require it's worthy of more thought. The cleanest application of sum check is exactly to compute inner products, where you compute the sum over X of like the multilinear extension of one vector times the multilinear extension of another vector. This is like the canonical application of sum check, and so here we just have a bunch of inner product claims. So this thing here, this batching procedure I'm describing, it just says apply sum check to all of the inner products, being claimed in parallel. And because you do it in parallel, that, at the end of sum check, you wind up evaluating each of the, multilinear polynomials at the same point. Like in parallel means you're using the same random verifier challenges in all of the instances of sum check. And so that reduces case 3 to case 1. But remember, so many polynomials at a single point. But remember that case 1 is always easy. And so you apply like the case 1, niceness, and that turns many polynomials at one point to one polynomial at one point. And so that's what's going on. And so you're, and because bulletproofs, this is also what bulletproofs is doing too. So your point is very well taken. It's worth thinking more. Like maybe it's silly somehow to apply, this batching procedure if bulletproofs is your commitment scheme, when bulletproofs itself is kind of doing the exact same thing. So I'll have to think about that more and see if anything non-trivial comes out of that.
Wow. Thank you.
Yeah. Thanks for more questions. Okay. So I'm just going to say a little bit about security, and then we'll wrap up. So sometimes I cover like a full security analysis in great detail, but I think that doesn't make the most sense today. But I do want to say a little bit about it. So let me just pull my notes here. Okay, so KZG, as I just described it, where the verifier, does two pairings, and the proof, the evaluation proof is just a single group element. So it is. I'm going to state something. It's not a strong enough security property to be useful in SNARK design. Okay, so it is binding, but we'll see. So I'll call it function binding. So this is not a good enough notion of binding for SNARKs. It is function binding, assuming what's considered a standard assumption. I can't really tell you much about the history of the assumption, but something called the D-strong Diffie-Hellman assumption. Okay, so this is considered a nice standard assumption. People are, theoretical cryptographers are very, very happy with it. And roughly what is function binding? It means if once the prover sends the commitment to P, G to the P of tau, which of course, a cheating prover might not actually, have any polynomial P in its head or whatever. There is some function, let me give it a name, F, that P is bound to. Okay. Meaning if the verifier later asks for, P of R, the prover does have to reply with F of R. If it can produce convincing evaluation proofs, and it can't break the assumption. Okay, but the reason this is not useful for SNARKs is we do not know, the analysis that we do not does not show that F is a degree n-1 polynomial or a degree n polynomial. It's just like so that is for every. So in order for the honest prover to be able to compute, G to the P of tau, P better be a degree n polynomial. Okay, but then if you go through the security analysis, that only invokes this, nice assumption that theoretical cryptographers are very comfortable with. You're not guaranteed in the, by the security analysis that the function the prover is bound to is actually a low degree polynomial, which is bad. That's not enough for SNARK applications. And so, basically what the way this works is you show like, suppose the prover can produce, two evaluation proofs, that pass the verifier's checks. One for the claim that P of R equals T1, and one for the claim that P of R equals T2. So you show you can take those two proofs and do some algebra with the group elements in those proofs, and break the assumption, break the D-strong Diffie-Hellman assumption. Okay. Okay, so there's some interesting binding property that comes from a standard, well-accepted assumption for the scheme as I described it to you, but it's actually not a strong enough binding property for the applications we all care about. And the intuition is I want to be sketchy here deliberately. You can read the book for full analysis. What is the cryptographic assumption, and the formal proof that you can take these two convincing proofs and break the assumption. But what's going on here is if intuitively is if P of tau does not if P of tau minus T does not actually if P of X minus T is not actually divisible by X minus R, then this W polynomial satisfying this equality here is not a degree n minus one polynomial. Rather, it is what W tau will be is like P of tau minus T over tau minus R. Okay, and so and this will not be equal to a degree n minus one polynomial at evaluated at tau. Okay, and so what's going to have to happen intuitively is in order for the prover to figure out like a W a tau in the exponent where this equality holds, like it really has no option but to divide in the exponent by tau minus R. Okay, but so to summarize, if the prover is honest, then W a tau is a degree n minus one polynomial, and the prover can just commit to it with the SRS, with the commitment key, because that's what KZG commitments, are designed to allow, is committing to degree n minus one polynomials. Okay, but if the prover is lying, then the W a tau that passes this check here, like the only way to compute it is to take P of tau minus T and divide it by tau minus R, all of that happening in the exponent. Okay, now if you go to the book and you look at what does the D-strong Diffie-Hellman assumption state, it literally states, this assumption literally states that it's hard, it's computationally intractable to do that division. So to compute, like G to the Z over tau minus R, given only the powers of tau SRS, and G to the Z. And so that's the intuition is like, if the prover's honest, W of tau is in degree n minus one polynomial evaluated at tau, and then, everything works out because the powers of tau SRS lets the prover commit to that W. But if the prover is dishonest, then the only way to get, a W tau that's going to pass the checks is to divide by tau minus R in the exponent, and the D-strong Diffie-Hellman assumption just assumes that's intractable. And intuitively, it's a reasonable assumption because, if you don't know anything about tau, how the heck are you going to divide by tau minus R in the exponent? Okay, so that is what you can prove from these sort of very well-established assumptions for the version of KZG commitments we've just discussed. But it's not a strong enough binding property because we really need to know that this F is a degree n polynomial. Okay, so what I want to say is with extra assumptions, which are sort of more controversial and much stronger than the D-strong Diffie-Hellman assumption, we can get the property we actually want, that F is actually a degree n polynomial. Okay, so I'm just going to say two things about these extra assumptions. Okay, so one is if you just do the analysis in something called the algebraic group model, and I'll say a couple sentences about what that is in a moment, then you're good. So the protocol I just described today gives you exactly what you want. And like not only, it gives you this, and in fact, you can actually efficiently extract, this degree n polynomial, from the prover, and everything is great. Okay, and so I think that's mostly what, deployments today, that this is where any kind of security analysis would work in. This algebraic group model. This is sort of spiritually. So here are the two sentences I want to say about the model. This is spiritually, similar to the random oracle model. So the random oracle model kind of says that the only attacks, possible on hash functions, just treat the hash function as a black box. That is, they only look at its, input output behavior. You're not going to attack SHA by like taking, a computer program, implementing SHA and like doing some crazy analysis on that computer program. The only way, yeah. So it's sort of, so the algebraic group model is kind of saying like, oh, the only way you can attack KZG commitments is to apply the cryptographic group operation as like a black box, where the algebraic group model doesn't let you, kind of like leverage, like details of how group multiplication is implemented in the groups we use or anything like that. How group elements are multiplied, via an efficient multiplication algorithm. Okay, so it's one of these idealized models that like only captures a subset of possible attacks, but a lot of people are comfortable that those are kind of the only attacks that that the groups we use today would be susceptible to, and so even though the proof doesn't allow all possible attacks, we're comfortable with that. So anyway, so if you're happy with the algebraic group model, you can use the scheme I described today unmodified, and get the security property that snarks need. There's another class of assumptions called knowledge of exponent assumptions. Okay. So this is different than the algebraic group model, but still somewhat controversial amongst, like theoretical cryptographers. These assumptions are what people call non-falsifiable, which is actually a technical term that I won't really get into. But generally, there are cryptographers that, well, certainly we prefer falsifiable assumptions as long as they're haven't been falsified, as long as they're plausibly true. So there are cryptographers who just consider that whenever you invoke non-falsifiable assumptions, that's pretty akin to just working in an idealized model, like the algebraic group model, even though it's not literally the same. Now, if you want to use knowledge of exponent assumptions, you'll actually need to modify the protocol that I described today and make it a little bit more expensive. So I won't go into details, but so even if you're fine with knowledge of exponent assumptions, for some reason you don't want to use the algebraic group model, you would, commitments, I think they become twice as big. So they're like 2 group elements instead of 1. And then I think evaluation proofs probably also become twice as big. And they're going to require some extra pairings as well. You might have to do like 3 or 4 pairings rather than 2 to verify them. Okay, and then finally, there's been some work which I'm not very well read on. To base security of KZG commitments. So this is very recent. And snarks that use them, like say Plonk, using KZG commitments. There's been some very recent work to base them on falsifiable assumptions. I think this is Litma and others. And so they may need other modifications to the protocol. I'm not sure. So this is more just a pointer. So as of a year ago, like these results are recent enough that, the last time through this group, reading group, I did not have to, they didn't exist, right? So this would have been the end of my summary, in previous iterations of the group. I would have said, look, you can use the algebraic group model. Then, you get everything you want security-wise for the protocol described today. You could use knowledge of exponent assumptions. This is still controversial assumptions, and you'd have to modify the protocol and make it more expensive. Now today I can say, actually, there are some falsifiable assumptions you can use. I do not know offhand to what extent they require modifying the protocol. They're also new assumptions, but they're very plausible, and they fall into this nice category of falsifiability that we prefer as theoretical cryptographers. So that's everything you need to know about security. Yeah. Okay. So let me leave it there. So to summarize, again, the evaluation proofs just have the verifier check that either when you apply the pairing to tau minus r, g to the tau minus r, and w a tau, you get out the same thing as the commitment and g. That's the whole thing, and this is fully secure. Gives you everything you want in the AGM, and been some progress towards using falsifiable assumptions in the last year. But my guess is that the evaluation procedure is not quite as simple and nice as what I have right here. But go and read the paper if you want the details. Okay, that's it. Any questions on the hand wavy security stuff?
I've got a question, but for the previous step. So if somebody have one for the security.
Nope, it's you. Go for it.
Oh, thank you. My question was about minus T that we.
Yeah. Sorry, I just forgot that throughout. I'm sorry about that. Yeah. Does that
Yeah, but
answer the question?
my question was how did we even get it? I kind of miss it.
Okay. So what this pairing check is doing intuitively is it's checking that tau minus r times w a tau.
I'm sorry. I'm sorry to interrupt.
Yeah.
Is the value of the polynomial at r
Yes.
at the random point?
The claim
Oh,
value. So the claim is that p of r equals t.
and how did we get it here?
So the prover. So it's like the snark verifier says, hey, I need to evaluate the committed polynomial at this point r. In the snark, really, you want to say that's really coming from fiat Shamir. So r would come from fiat Shamir hashing, like the commitment and anything else that kind of comes before the selection of r in the protocol. And the prover comes back and says, hey, you needed to evaluate the committed polynomial p at r, and I claim the evaluation is t. Let me prove it to you. And the proof is this g to the w of tau. That's the proof. And then what the verification procedure to check the proof is this pairing check. And so, the same way, remember the verification key is g and g to the tau. Right. And so it might be a little confusing, like how does the verifier get g to the tau minus r? How does it get g to the p of tau minus t? And the answer is it gets g to the tau minus r here by taking g of tau and multiplying it by g to the, minus r. Right. The verifier knows r, the verifier knows t. It doesn't know tau. It does know g of tau. So, it can subtract r from tau in the exponent with one, kind of group multiplication. That's how it gets g to the tau minus r. And it gets this by taking, it does know g to the p of tau. That's the commitment to p. And it knows t. So, it can multiply. Yeah. So so any kind of subtraction by public quantities can be done in the exponent by the verifier directly. And that's why we can do, get tau minus r in the exponent for the verifier. And that's why we can get p of tau minus t in the exponent, because the verifier does know r and does know t. Those are just, known to the verifier.
Yeah, it makes sense. I guess I just got confused because at some point there was no minus t, and
Yeah,
then it
sorry.
appeared. Yeah,
Sorry. Yeah.
makes sense perfectly now. Thank you.
Okay. More questions?
Yep, someone's coming.
Hey, Justin.
Hey.
Can we get a bit more into the issue about the invisibility of because of the assumption when the prover is dishonest?
Yeah. So go ahead. So is there a specific question?
No, just know a bit more about the details of why is it invisible exactly, and
Okay.
how does it break the assumption?
Yeah. Okay. So and so the assumption you're interested in hearing more about is this D strong Diffie-Hellman assumption, which is only enough on its own to guarantee function binding.
Yeah.
Yeah. Okay. All right. Yeah, I'm happy to say a little bit more about that. Let me just pull up the full assumption here. Because once the assumption is stated, it's like very straightforward to show that, kind of two convincing evaluation proofs will directly break the assumption. Let's see. Here we go. Okay, so the D strong Diffie-Hellman assumption states the following. So, the attacker has to be given the powers of tau SRS because the world is given that SRS. So given g to the tau, g to the tau squared, g to the tau to the n, and so anybody who wants to attack the protocol knows that string. They don't know tau. So yeah, it is intractable to output any pair of the form z g to the 1 over tau minus z. Okay, and so intuitively, this is like saying, dividing by tau minus z in the exponent is intractable. And intuitively what's going on is look, the SRS gives you the power the ability to kind of take any linear combination you want in the exponent of positive powers of tau, right? So you can commit to, sum over I of g to the ci tau to the I for positive powers of tau up to power n. But this is a negative power tau, right? This is 1 over tau minus something. And so, the SRS, by not leaking any information about tau besides, these powers in the exponent, it shouldn't give you any ability to deal with negative powers of tau like this. So that's what the assumption just assumes, and it seems very plausible. Again, I don't quite understand the full history. Apparently there was something called the strong RSA assumption from 1997, and then this version of it was this is like a tailoring of it to elliptic curves rather than RSA, which was given by Bonnet and Boyan in 2004, which predate KZG commitment. So it's not like KZG cooked this up themselves. Anyway, so that's the assumption. Seems very plausible, but I can't say much more about, why people, put it forward in the first place. Okay. And in order to have so in order to produce two convincing proofs, one establishing that like P of R equals T1 and the other establishing that P of R equals T2, like what are those two convincing proofs? Well, they, rather than writing out all the pairings, I'll write out what the pairings are meant to check. Everything's happening in the exponent here, right? So the proof of this is establishing that, what is it, tau minus R times, say the proof here is W1 times W1 of tau equals P of tau minus T1. And the second one establishes that tau minus R times W2 of tau equals P of tau minus T2. Okay, and you can just do some algebra here, which so you would take these two proofs. The two proofs are W1 of tau and W2 of tau in the exponent. So all the algebra I'm about to do would really happen in the exponent. But yeah, so can I do this online? It's not that bad. All right, yeah, you do some basic linear algebra, which I can try to do in a second. But you wind up these two equations imply that 1 over what is z here? Z winds up being z. Okay, my notes. We'll figure out what z is in a second. 1 over tau minus z equals W of tau, W1 of tau minus W2 of tau over, what is V the claim value? Yeah, over T1 minus T2. Okay. So I have to figure out what the Z is. So I'll tell you what this is in a second. Okay, but basically so once I give you, these two equations that hold, which, are just capturing that the proofs pass the verification procedure, you can, combine the two equations to conclude that this holds. Okay, again, this is all, really happening in the exponent, and I haven't even told you what the z is because I don't see where the book defines it, unfortunately, but I'll figure that out in a moment. And so, but the verifier can compute this right? So the verifier was given g to the W1 of tau in the first proof. It was given g to the W2 of tau. And, T1 and T2 are public. So it can compute g to the T1 minus T2. So it can get this right-hand side in the exponent. So that'll equal g to the W1 of tau minus W2 of tau, T1 minus T2. Okay, and so once I tell you what the z is, which, it must be some combination. Maybe it's just some combination of R and something else. Maybe it just is R even. I can't do the algebra on the fly. That's how you break the assumption. So, it would output whatever the z is, comma, this quantity right here. And that was this quantity is exactly this g to the 1 over tau minus z that the assumption assumes no one can efficiently compute. Now, the reason this security analysis is not enough for SNARK design is it didn't tell us any. All this says is at any R, there can be at most one value T1 that an efficient prover can open, P of R to. It does not tell you that as you go over many different values of R, all of the opening, all of the evaluations lie on a good degree n polynomial. And to get that, you need, until a year ago anyway, you certainly needed much stronger assumptions. And the new works, I guess, make some progress towards getting something like this property, even without moving to non-falsifiable assumptions. Was this interesting, helpful at all? Should I figure out what this Z is? Maybe it is just R.
No, I think it's fine. I'm struggling to understand, why are we like how is the prover evaluating this same random number and gets like two different values?
But it doesn't matter. What this is saying is, any prover that is, the way to think of this is, suppose, what does it mean for KZG commitments to not be function binding? It means that there's some evaluation point where the prover is capable of providing more than one answer to the evaluation query. Okay, so what I'm just saying. So say it can provide two answers to the evaluation query. Call the first answer T1 and the second answer T2. I don't care where they came from. It's just, if the prover was capable of answering, the one query with two different answers, that means it's capable of quickly computing a convincing proof for each of the two answers. And I can just take those two proofs and, combine them just like this, just divide them. And then, divide that result by this other value that everyone in the world knows, and thereby compute this quantity that the de Strong Diffie-Hellman assumption assumes no one can efficiently compute. So did that clear it up? It's like, if there's any evaluation query that the prover is capable of providing two different answers to, that itself violates the de Strong Diffie-Hellman assumption. That's what this analysis says.
Okay. So it's like we take the other way around and we prove that since this cannot be broken, then it cannot give these two evaluations, right?
Yeah, exactly. Yeah. If it gave the two evaluations, then we could break the assumption. Yeah, for just giving two evaluations and the proof for each of them. Yeah. Exactly.
Okay. Thanks. Perfect.
Yeah. And it's a little funny that it's such a simple analysis, but it doesn't give you it gives you something interesting, but it's not interesting enough for snarks. Because it doesn't tell you anything about the one. So it says there can only be one value that the commitment can be open to for any evaluation point, but it doesn't tell you anything about that value. It just says there can only be one per evaluation point. So it's weird. I've always had a little. The commitment scheme is so simple, and this evaluation proof is also this security proof is also so simple. It's always felt to me like there should be, like basically the recent papers that came out have always felt like those papers should be writable, but it feels like it shouldn't even require new research papers, and yet it does seem to. So that's always kind of puzzled me a bit. I've never dove deep enough to figure out why it's as complicated as it is to establish security of such a clean and simple scheme, security of the kind that's needed for snark applications.
Okay, thank you so much. I think set is R, right?
Probably. Yeah, we could. Yeah, I mean, we could just do the algebra. Yeah, you must be right.
Yeah, just subtract, and I think it works.
Yeah, great. Yeah. Yeah, and this is the security of Schnorr's protocol, like all of the security proofs. They always go like this way. It's like if the prover can break binding, it can produce two proofs. Each pass the verifier's checks. The verifier check is really just establishing some equality holds. That gives you two linear equations that you can then use to solve for something. So it always goes this way, and it's just very annoying here that this recipe doesn't tell you anything in this case about what value the prover is bound to. But it is, yeah, you're right. It's just R is just Z. It's the same thing, and it's very simple algebra to go from the two proofs to the violation of the assumption. Any more questions? All right. So I think next time we will discuss Dory. I'll probably try to keep it to one session, even though I'm a big fan of Dory. I'm gonna insert following that. I have some new work on like memory checking, lookup argument things. So I'll insert a session on that just because I'm excited about it, and I also wasn't happy with my coverage of lookup arguments earlier in the reading group. And then we'll probably there's not too much left after that. We'll probably turn to maybe growth 16, and then maybe recursion and nova and folding schemes. And I think that's everything. So anyway, but the next two sessions, Dory for one, and then new memory checking arguments for the next one. Okay, so happy New Year, welcome back, and look forward to seeing you next week.